I've been working on modifying the Ramsey amplifier, doing some things with regard to the analog discovery, including looking at some issues that El Paso Tube Amps has brought up about the voltmeter, and finally trying to address a problem having to do with the audio analyzer suite no longer being available. So this is a little update on those three issues. Most of the time I'm going to be spending on this Ramsey amplifier, but I will touch on those other two issues in passing. The Blue Glow Electronics is put out a video, I think yesterday, about the audio analyzer suite. As you may know if you've watched his channel, he's been trying to build a sort of standalone unit using the analog discovery and the audio analyzer suite. And what he discovered was that the audio analyzer suite is no longer available. I can confirm that. I've actually been working for several weeks on trying to figure out what went wrong and how we might be able to get that piece of what I consider excellent software back up and available to people to use with the analog discovery. I've been pretty unsuccessful. I've tried emails to Jake, and by the way, I think Jake is a good guy. I know there's some stuff on a few places on the web that imply that there might be something going on there. I don't think so. I think he's a good guy. His website seems to be down, and he does not seem to be getting email any longer at the address I have. So that approach has not worked. I've been looking at working with Digilent to perhaps, because somebody mentioned that they thought it was a result of Digilent objecting to his use of the software development kit or something. I have sent an email to Caitlin a little over a week ago at Digilent. She hasn't responded yet, but I'm hoping that we'll get some response from her. But once again, I don't think it's Digilent's fault. I think for some reason Jake's website just is down, and if he can get it back up, I'm sure he'll put the audio analyzer suite back on there. At any rate, in the meantime, I've been looking at some alternatives, and I'm not ready to go into any of those at this point, but I do want to kind of update people on the analog discovery and the fact that the audio analyzer suite is not available at the present time. If you downloaded it before you bought your analog discovery, it should still work. At least mine still does. But for people who are buying new analog discoveries expecting to use the audio analyzer suite, unfortunately I can confirm what Blue Glow says in this video, and that is it is no longer available. In this video, David at El Paso Tube Amps was looking at the accuracy of the voltmeter in the analog discovery 2, and he found that it is pretty inaccurate as you go up in frequency, and in fact you can't even use it much above a kilohertz or so with any kind of accuracy. I have done similar tests on my voltmeter. I had never seen this before, but when David brought it to my attention, and I found basically the same thing. So let me show you what I did to measure that, and also what I did to try to solve the problem. Here is I'm using the Ramsey amplifier just because it happens to be out on the bench, but the verification of the problem with the voltmeter in the analog discovery. You'll notice that channel 2 has a value of very, very close to 1 volt RMS on channel 2. So now what I'm going to do is I'm going to run the frequency from 1 kilohertz up to 10 kilohertz. And you notice that the level dropped substantially to 173 millivolts, true RMS. And the channel 1, which is the output of the waveform generator itself, dropped as well. So what this shows is that the voltmeter is not accurate at any frequency above about a kilohertz or so in terms of RMS. So let's take a look at a workaround, if you will, for the same for doing the same measurement. This is the same setup. I haven't changed the volume controls or anything. So now what we're going to do is we're going to go over here to View, and we're going to click on Measurements, and we're going to go over here to Add, and we're going to add a defined measurement on channel 2 of, and in this case we want a vertical measurement, and we want AC RMS. We're going to add that. We're also going to add the same thing on channel 1, and now we'll close it. And you'll notice up here, now this is still at 10 kilohertz. You notice that it's now, let me zoom in so you can read that better. Is 1.03 volts RMS. Now what I'm going to do is I'm going to go up in to, let's see, we'll go to 50 kilohertz. And you notice it's still reading 1.03 volts RMS. Now what I'm going to do is I'm going to adjust this just about the best I can do right there, 1001. And that's at 50 kilohertz. Now I'm going to go down to 1 kilohertz, and you notice it's 1.049. So what this shows us is that if we use the measurement function of the analog discovery oscilloscope channel, you get a much more accurate RMS value, and I hope you'll pardon the beeping. That's my multimeter telling me that I haven't paid it enough attention, so it's going to turn itself off. And this is a much more accurate way to measure. And what I have found in general is that because the scope channel is calibrated, but the voltmeter channel is not, even though they use the same hardware. In fact, you can't use the scope while you're using the voltmeter and vice versa. But what you can do is you can add voltmeter measurement to the scope channel. So you can both display the waveform and read the AC RMS, or for that matter any of those other measurement values, by simply adding measurements to a scope channel. So you could either consider this to be a workaround or an answer to the question of the voltmeter inaccuracy in the analog discovery. I had frankly never seen the problem that David at El Paso Tube Amps found, because I had never used the voltmeter. I always just turn on measurements in the scope, and I had found them to be pretty accurate up to around 10 megahertz or so. Now once again, when you get above 10 megahertz, as I've shown in some other videos, the analog discovery begins to have some issues. In fact, when you get above 20 megahertz, you can't really depend on the signals, especially if you're using the flywire. But if you're using the BNC board and some good probes, you can use the analog discovery scope channel to measure RMS voltages up to and beyond 20 megahertz. At least the analog discovery 2 that I have will do that. Now I've repeated this on the analog discovery 1, and once again, using the same conditions, I have found that it also is fairly reliable up to a little above 20 megahertz. So I hope this will be useful to those people. I understand from the video that David left last night, I think, the he has talked to the Digilant people, and they have confirmed that they will try to fix this in a subsequent video or a subsequent software update. In other words, this problem with the voltmeter. But if you're looking for a way to measure AC RMS accurately using the analog discovery, I suggest you simply turn on the measurement function for that scope channel. Here is the modified Ramsey amplifier. I have it hooked up the same as before, once again using a 9-volt battery. Back there are the two 15 ohm resistors that I'm using as a load. And over here is the analog discovery 2. And it is connected to both inputs. In other words, the waveform generator is driving both amplifiers at the same time. And then the output is connected up to those 15 ohm resistors. And we're monitoring those on the scope of the analog discovery. So in other words, waveform generator 1 is driving the amplifier and also connected to channel 1 of the analog discovery scope. Channel 2 of the analog discovery scope is connected to the output of the amplifier across those two, across the one 15 ohm resistor. Right now I'm just using the right channel. So let me show you what changes were made in the circuit. The changes that I made is I changed this 2 ohm resistor to a 10 ohm, which is what is recommended by the manufacturer. And that should improve the high frequency response. If you recall, if you watched the part 2 of this Ramsey amplifier, we found the frequency response which went out beyond 100 kilohertz, but began to fall off about between 120 and 150 kilohertz. I've also changed this output from 220 microfarads, this capacitor, to a 1000 microfarad, which was another suggestion I made near the end of part 2. And finally, I changed this 10 microfarad to a 100 microfarad. And the reason I did that was to change the phase response of this amplifier at the low end. It will have some effect on the low end frequency response, but by going to a 100 microfarad here, it makes the phase response of the input relatively insensitive, for example, to whether you switch the sibilance control and to where you have this pot set. One of the problems with this particular circuit is as you move the pot from the top to the bottom, the volume control, the impedance of this line of this point changes from 10K to ground to close to 0 ohms. And although it has an isolating resistor in here, I wanted to make sure that the phase shift across this capacitor is as low as possible at the low frequencies. So anyway, enough of that. Now let's look at what it did on the network analyzer. Here we have the network analyzer of the Analog Discovery 2 displaying the gain and phase of the modified Ramsey amplifier. At the left end is 10 hertz. At the right end is 200 kilohertz. The bottom trace is the phase, and you may notice that the phase shift at 10 hertz is much less than it was with that 10 microfarad input capacitor. The gain is, I have it set so that there's just under 10 dB. Let me reduce that to 9 dB. Approximately. That way it'll be easier to read. Okay, it's about 9 dB of gain now at the midband. This is 10 dB at the top, this is 9, and then 8, 7, 6, and so on. So over here, the 6 dB point will be the 3 dB down from mid. So you see it's just a little above 10 Hertz now. You'll notice that the high frequency response is better. Instead of dropping off at about 150 kilohertz, which would be about here, it drops 3 dB a little above 200 kilohertz. And that's partly due to the fact that I changed that 2 ohm resistor to a 10 ohm resistor, which helps the high frequency response. Now understand, the amplifier will be a little less stable in terms of the square wave or whatever analysis. But we'll take a look at a square wave here in a second and see if we're getting any significant problems there. But basically what this shows is that we were able to lower the low frequency response of the amplifier primarily because we changed the output capacitor to 1000 microfarads. We were able to raise the high frequency response of the amplifier slightly because we changed the suppression resistor from 2 ohms to 10 ohms. And we were able to improve the phase shift at the low frequency by changing the input capacitor from 10 microfarads to 100 microfarads. So now let's see if we have introduced any instability in this amplifier by changing and looking at a square wave analysis. We're now looking at the square wave analysis of this amplifier. The yellow trace is the output of the waveform generator. The blue trace is the output of the amplifier. And you'll notice that there is some loss of the edge here. That's basically the high frequency cutoff. This is a 1 kilohertz square wave. Let me go down to about 200 microseconds per division and you can see the square wave. And we go up now to 10 microseconds per division and you see there is little or no overshoot or ringing, which is one of the things we would be concerned about. The other thing is that the rise, let me go to an even faster 1 microseconds per division. You'll notice that even though the waveform generator does exhibit some ringing, the amplifier is very stable throughout its entire rise time. And what this shows us is that we have not introduced any significant instability problems by going to the 10 ohm resistor for suppressing of oscillation or unwanted transients in the output of the amplifier. So I think what we have shown is that this is a superior amplifier to the one that Ramsey supplies. We were able to get to this point by changing the output capacitor, the input capacitor, and the suppression resistor. So I hope this is useful to those who might be interested not only in building this amplifier, but also the general ideas of what we're trying to accomplish here with regards to any LM386 amplifier, or for that matter, any audio range amplifier that you are working with. The same basic principles would apply.